Hey, good morning, everybody. This is Mr. Ainsworth, and I really mean good morning because it's 5:51, and we are in Lesson 8 Linear Programming, Part 3, example number 3 here, and I'm going to go through another example with you guys about this time manufacturing and making furniture. So let's read the problem here. Let's dissect it and take all this information and organize it in the form of a table first and see what we have. All right, we have two workers, and they're Juan and Ava. Yes, I said Juan and Ava. They get $100 for making a table. That looks like a profit. Okay, so they get $100 for making a table here. They get $80 for making a chair. That's their income, actually. So it doesn't say profits. That's what the money that they bring in is called income. And sometimes after you take that income and you subtract the cost, you get what's called profit. So sometimes they call it profit and sometimes they call it income. It all depends on what's going on. This time, this is the income. So right now, I already know that for a table, let's highlight these here. We've got a table here. We've got a chair here. I know that my income for a table is 100. So income right here, 100 for a table. I make that much, or Juan and Ava make that much, and they get $8 for a chair. So what you want to do is read and bring the information over here at the same time. That's usually what I do. On average, Juan must work 3 hours and Ava 2 hours to make a chair. Ooh, so this information is about a chair. So we got 3 hours for Juan and 2 for Ava. So for a chair, let me see, we've got 3 hours here. For Juan, and also 2 hours for Ava. Very good. All right. Now Juan must work 2 hours and Ava 6 hours to make a table. So now we have information on the table. So we have 2 and 6. So we have 2 hours for Juan and 6 hours. Takes her a little bit longer for Ava to make a table. All right. Let's see what the time available is. If neither one of them wishes to work more than 42 hours per week. Okay, they don't want to work 42 hours per week. How many tables and chairs should they make each? Let me see. X, we'll call it tables. Y, chairs. How many should they make? How many? That is a variable question, okay? To maximize their income. We want to maximize income here. So we want to maximize income. We've got to do that. I said X is tables, so this is X equals number of tables here, number of. Y equals the number of chairs, number of chairs. And we're good to go, and we need some, we have time available. Let me see, they don't want to work more than 42 hours, so that means they've got to work 42 hours or less. So less or equal to 42 hours available. They don't want to work more than that. I mean, that's a long week as it is. All right. Usually people work only 40 hours a week, but in this problem, it says that they don't want to work more than 42 hours. Well, that means less than or equal to 42 hours for both of them. So we're going to put down less than or equal to 42 hours for both Juan and Ava. So once you get your information in your table here, what you want to do is interpret the problem into a system of constraints. All right, but first we have to write the question down. It says how many hours? Oh, actually, it's already written down. So how many not hours, but tables and chairs should they make? See, this is the question. So I'm going to highlight this. How many tables and chairs should they make each to maximize their income? All right, so that's the big question. So what we're going to do is we're going to let X equal the number right up here of tables, because they don't know how many they should make, you know, to maximize this situation. So you let X equal the number of tables, Y equal the number of chairs, just so that you can start the problem. All right, now time to make some constraints and limitations. So what we do is bring this down here, take a look at Juan here. I know that for every table it takes him 2 hours, and for a chair, it takes 3 hours because chairs are a little bit more complicated because they got different curvatures and everything. So for every table, it takes him 2 hours, and for every chair, it takes him 3 hours, and he doesn't want to work more than 42 hours. So we got to take the time it takes per table, multiply it by the number of tables, which is x in this case. So 2 times x here, plus 3 hours per chair times the number of chairs, which is y in this case, because we don't know how many, it's got to be less than or equal to 42. Remember, it takes 2 hours for one table, and if there's 2 tables, 4 hours, 3 tables, 6 hours, 4 tables, 8 hours. You got to multiply those values here. So I've got to take the number of tables, multiply by the number of hours per table. So 2 times x here, plus 3 times y is going to be less than or equal to 42. So for my Juan's time, this is his constraint, I've got 2 times x, that's the time it takes him for tables, plus the time it takes for him to make a chair, which is 3 times y. So 3y has got to be less than or equal to 42. Now Eva has a constraint too. She doesn't want to work more than 42 hours either. Now for one table it takes her 6 hours. So you've got to take 6 hours per table times the number of tables, so 6 times x, plus her time to make a chair, 2 hours per chair, times y, so 2y here, is got to be less than or equal to 42. So 6x plus 2y is going to be less than or equal to 42. Of course, these values, the number of tables and number of chairs, can't be negative. All right, that wouldn't make any sense. So we have to write our non-negative constraints here. So x has to be greater than or equal to 0. Y has to be greater than or equal to 0, because it can't be negative, guys. Now, remember our objective, our goal, objective, all right, same thing here, is to maximize the income. So what I need to do now is I need to take this information right here and write my objective function, which is my goal function, okay? Objective is goal. And I know that for every table they make $100, and for every chair they make 80. So I got to take the amount of money they make, multiply it by how many they make, amount of money they make, multiply it by how many they're making, which is x. So I got 100x right here, plus $80 times how many they make, y, to get my total income. So I have an income function here. So my income is going to be $100 right here, times how many I make, x, plus $80 times y, so plus 80y. Okay, and that's income, so my, just call that I. I equals 100x plus 80y. That's my objective function, or my goal function, so that I could use it to maximize the income later on. But I got to find the corner points first. So I've got to graph these right here. I'm going to call this inequality 1, this one number 2. I'm going to do what I always do. I'm going to bring them off to the side and start isolating y here, which is one of the methods used to graph functions. Not the only one. I could use intercepts if I want. I do that personally, but I'm going to do this here. So I've got 2x plus 3y is less than or equal to 42. Got to subtract 2x. And I get 3y is less than or equal to negative 2x plus 42. After dividing by 3, let's see what we have. We've got y less than or equal to negative 2/3 x plus 14. Because you got to divide here by 2. Or excuse me, by 3. And 3 times 14 should be 42. So I've got my slope here, I've got my y-intercept here. And inequality number 2, I've got to do the same thing. So I've got, what do I have? So I've got 6x plus 2y is less than or equal to 42. I've got to subtract 6x here. I've got 2y less than or equal to negative 6x plus 42. I've got to take everything and divide by 2. So y is less than or equal to negative 3x plus 21. That's my second inequality, with my slope of negative 3 and my y-intercept is 21. All right. So now what do we do? Well, we got to decide, do we have on this graph enough room to graph a y-intercept of 21? This is 21. Just let me change this, make it look a little bit better here. 21. That's my y-intercept. So 2, 4, 6, 8, 10, 12, 14, 16. Nope, going to have to change the scale. So change the scale on this one here. So 2, 4, 6, 8, okay, 10, 12, 14, 16, 18, 20. So I'm I change the scale to 2 here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and then 24, 26. Very good. So this one's 22, so there's 21 right there. Right in between 20 and 22. All right. And same thing here. So I'm going to start graphing now so I can find my corner points. So let me label this here first. 4, 8. That's not correct here. 12. Count by 2, 4, 6, 8, 10, 12, 14, 16. And then this would be 18, 20, 22, and so on. All right, so there's my x-axis, and my y-axis is up here. All right, so here we go. I'm going to graph the first inequality at 14 here. So here's 14. So point there, down 2, right 3, down 2. Let me see, we're counting by 2s. So down 2, right 3, down 2, right 3. You got to be careful when you change the scale because we're counting by 2s now on the scale. So down 2, right 3, down 2, right 3, down 2, right 3. Got to keep on repeating this. Down 2, right 3 here, and then down 2, right 3, right there. So right, let me see, that's 20, that's right at 19. So take the straight edge out, go ahead and graph your line here. Make it really nice and accurate right through 19. There we go. It's less than or equal to. Let's see. Let me double check that. Okay, I'm back now. What I found out was I just mislabeled the x-axis here. So change, if you're looking at my x-axis here, I put different numbers, I just fixed them. So 16, 18, 20, 22, 24. So I fixed my numbers on my x-axis so that when I double check my work, it all makes sense. So it intersects the x-axis here at 21. Right here, this is 22, and between 20 and 21 is, excuse me, between 20 and 22 is 21. So we're all good now. So this is inequality 1, it's less than or equal to, we graph down. Alright, so inequality 1 right there. Second one, I'm going to switch colors to blue now. I'm going to start at 21. 21's right up here. And I got to go, let me see, down 3, right 1. But this is a scale of 2, so what I'm going to do is I'm going to go down 6, right 2. Just double each here to make it easy to count by 2s. So from here, from 21, I got to go down 6. So 2, 4, 6, right 2. Alright, or you can count down 3 and right 1. 1, 2, 3, right 1. 1, 2, 3, right 1. Okay, and continue. And then we're right here, that's where they intersect. And then down 3, right 1. Down 3, right 1, down 3, and we'll just continue doing this here. Right 1, down 3, right 1. So intersect, it looks like, let me see, this 6 and that's 8, that's 7. So that looks right. So let's go ahead and get your straight edge and graph that line there. And it's less than or equal to, so we're going to go below. This is inequality number 2 now. Now my non-negatives, let's see, I've got this one right here, it's a vertical boundary line to the right, okay, to the right of the y-axis right here. It's all to the right. I've got my other non-negative constraint, my horizontal boundary line here. It's got to be above the x-axis. Alright, y is greater than or equal to 0 is above the x-axis. Y greater than or equal to 0. So where is it? Where's the feasible region? Well, it's got to be where they overlap, so it's got to be in here. Where do all those colors overlap? The red with the green, with the blue and the black, they all overlap in here. So there's my feasible region. I've got some corner points right here. I've got A here, I've got B here, and I've got C, which is right here, and I've got D at the origin, which is not going to be a solution. All right, because I got to make something here, guys. We got to, Juan and Ava's got to make tables and chairs, so the origin is never going to be a solution on the maximization problem. All right, so what is A? Well, it's 0, 14. All right, B, what in the world is B here? It looks like 3 up 12, so 3, 12. Let me just check that. 3 here, 6, 12, 36, 6 and 36, 42. It's on a line. So 3, 18, 18 and 24, 42. Yeah. So that looks good. C is 7, 0. So 7, 0. Put a 7 here, 0 here. You get 42. That looks good. So C is looking good. So there's my vertices. But the question is, which one of these maximizes the income? I don't know. So what we need to do is go further here. We need to take our vertices, bring them over here, substitute them in our objective function, and see which one maximizes the income for Juan and Ava. So let's go ahead and record these over here. C is 7, 0. Let's bring our objective function in. Okay, income is equal to 100 times x plus 80 times y, where x here is the first coordinate, y is the second coordinate, and remember we're substituting in. We're going to evaluate the corner points to see where our maximum income lies, and then we'll interpret the solution. So for the first one here, we've got 100 times x, which stands for, let's go up here, which stands for the tables. So it's tables and chairs. So these are tables. All right, the y coordinates are chairs. All right, number of tables, number of chairs. So 100 times 0 plus 80 times 14, that'll give us our income for the first corner point. Now that's 0. We got 80 and 32, 112 with a 0. All right, 1,120 here. So multiply 80 times 14. Just do it in the margin, 80 times 14, and go for it. All right. The second one, the income, is 100 times 3 plus 80 times 12. What's that? 300 plus, let me see, 8 times 12 is 80 and 16, 96 with a 0, so 960. All right, and then you add 300, 900, 1200, so 1260. Ooh, look at that. 1260 is bigger than 1120, so already I can see that this would be a better way to handle it. Juan and Ava needs to build 3 tables and 12 chairs so far, unless this beats it here, so I don't know. 100 times 7 plus 80 times 0, that only gives us $700 income. So the maximum here, the maximum income that they can get is found here if they build 3 tables and 12 chairs. So Juan here and Ava needs to build, all right, 3 tables, all right, 3 tables and 12 chairs to maximize their income. Maximize income, which should be $1,260. Okay? If they do that, they'll get the most money. If they don't do that, they're going to get less. I mean, there are other ways to do things in their business, but if they want to maximize their income, they're going to build 3 tables here and 12 chairs. That's the optimal solution. Let me see, optimal solution to the problem is if they do that. Okay? There's problem number 3. I'll see you in number 4 next time. Work hard, do your best, and try the next problem.